All right. Thank you for coming, everybody. Today we are going to talk about the last thing we talked about in EMG lecture. That is the wiring diagram. Using EMG, was drawing a wiring diagram of human nervous system. Now, first of all, why do we need it? Why do we need to draw human nervous system? I'll tell you a few things about it, because it's the, first of all, understanding of the operation of the nervous system. You will need to understand the whole wiring diagram of the human nervous system. For instance, if one of these lights go off, and you can't really, by changing the bulb, you can't really fix it, you need to know the wiring of it, where the actual wire goes, where the fuses are, where the switches are, etc. So for the, similarly, for human nervous system, you need to know and understand the entire system, so that if something goes wrong, like there's demyelination, there's a motor neuron disease, clinical neurology point of view, there are various disorders where you actually need the wiring diagram so that you can check which part is actually going wrong. So for those kind of reasons, understanding of the operation, clinical neurology point of view, neuromuscular disorder point of view, demyelination point of view, conduction block point of view, you need to find the wiring diagram of the human nervous system. Right. Now, nervous system you can find, I will just draw what it really we are talking about. Probably start from here. So this is the spinal cord. It's got a hole in the middle, spinal, it's a spinal fluid. And you've got the ventral horns and dorsal horns. And if you've got, for instance, a receptor, it goes into the spinal cord, but just before going in, it leaves this soma, the soma of the neuron, outside, which is called the spinal ganglion. And then within the spinal cord, you've got the gray matter and white matter. Gray matter is where the cells are, and white matter is where the conductions are, where the axons are. So it goes into the gray matter and changes into various interneurons and goes towards the motor neuron, which is in the front ventral horn, and that goes into the muscle. So that's what we talked about last time, the muscle part of it, how we record it from the muscle, etc. So we called it EMG, electrical activity of muscle. But in the same time, this goes to the other side, and usually it does the opposite on the other side by activating in the final stage an inhibitory neuron, interneuron, and goes to the other sides of muscle, and it generates an inhibition there while it's exciting on this side. So it could be vice versa, depending on the receptor. But in the same time, this goes into the white matter, spinal cord, and goes up to the thalamus, and then changes neuron there and goes to the sensory cortex, which goes into motor cortex, and then comes down to the spinal cord, again affecting these various interneurons. So this is really the system we need to find out. So when we talk about wiring diagram, this is the diagram we are talking about. We need to understand what goes where, what kind of synaptic potentials are occurring, how many interneurons exist, what's the conduction velocity, etc. So this is actually extremely easy to do in animals. In animals, you can dissect the fibers so that you know if it's an A delta fiber, for instance, or C fiber, or a alpha part, a beta fiber, etc. And you stimulate it mechanically or electrically and record by putting needles into various stages. You can actually work out the wiring diagram in an animal quite easily. But in human, you can't do it. That's what we want. We want to actually understand human, not cat or rat or whatever.
Or
so
llamas.
what do we do? What do we do? Now animals, as I said, is easy, but in animals there's a problem, the fact that they are anesthetized, and anesthetics actually, by matter of fact, they work through synaptic changes. That's how they lose their consciousness when animals fall asleep. So these are all synapses, so they'll all be altering their responsiveness. So do we trust the animal findings regarding wiring diagrams or not? I think that's the question. So if we are doing these experiments on human, we are really working on the subject we want to understand and also subject we want to treat.
And we can't.
But how do we do it? How do we do it? This is the problem. Now I'll go through the methods that we use. And methods obviously in human it has to be indirect. We can't put stick needles into interneurons, spinal cord or brain. You can't do it. You cannot do it. So we need to be clever.
We can do it on Imran though, right?
All right.
Can we-
Excepting Imran. Now, we need to be lateral, we need to be clever, we can't anesthetize, we can't stick needles, but
Just
we
take
can
care
do
of me for
things
60 years.
and we almost get the same results. I'll get you at the end of the lecture that to make you understand that you actually almost get the same results as in animals without anesthetics, but indirectly thinking lateral in human. Now, first thing I need to mention here is really the aim in our experiments is to understand the circuitry, but for that we've only got two things. We can, into this black box, we can send an input, we can get an output, wrong way around, output, and in the middle we've got a big question mark. That's all we can do in human. But the fact is we are working quite indirectly. Our indirect method has to be correct. It has to be tested. It has to be proven to be representing the system. So that's what this talk is all about. Trying to say that we understand the middle or question mark, black box, because our methodology is well tested. All right. So, first of all, I start from the problems of human. So, input problems. We a little bit talked about output problems because we talked about surface EMG and single model units. I'll come back to them again. But I start from the input problems. As I said, in animal, you can dissect the nerve quite easily because it's anesthetized, there's no pain. You can dissect the nerve and put it onto the electrode, work out its conduction velocity by stimulating in one end, recording from the other end, and let's say, oh, this is a beta fiber. Let's find out what a beta fiber does. So stimulate and record from various points in the spinal cord or the cortex, find a circuitry, fine. But how do you do it in a human? Now I'll give you a few examples on this. If, for instance, you want to stimulate pain fibers and want to find out about the pain circuitry of human being, how do you do it? You can stimulate it mechanically, because normally you get mechanical stimulation, you prick yourself with a needle. But are you going to be able to do that? You have to do 100 times pricking needles into the person. But in the same time, while you are doing that, you are also going to affect other receptors in the skin, touch receptors, temperature receptors, etc. So you can't do it as easily as animal. You have to be more lateral than that. How do we do it? Electrical, we can do it. Now, but electrical stimulation, I'll tell you the problems of electrical. Let's go there. Electrical. Now, electrical stimulation, if you put electrical cathode and anode, pass current between them. If you put it on a nerve, for instance, you put it on radial nerve, ulnar nerve, or median nerve, you have certain problems. We'll look at them first. So this is the nerve, and nerve has inside negative, outside positive, as you know, membrane potential. So this side is the same. So if I put cathode and anode on top of it, this is cathode, this is anode. What you do is, when you pass the current between them through a stimulator, what you do is you increase these around them. So effectively speaking, you are trying to depolarize this area, because outside becomes negative, inside, relatively speaking, becomes positive. So you generate an action potential here, which moves in that direction, but not into that direction, because you generate here hyperpolarization effectively. So if you draw membrane potential, this is depolarization on this side and crosses the threshold, becomes an action potential. But on this side, you really generate a hyperpolarization, move right away from the threshold, and therefore you cannot generate an action potential here. So it is called anodal block. Right, so this is one problem of stimulation in human. In animals as well, this is the same. Anodal block issue is quite important, especially when you are stimulating and trying to get H reflex. If you want to send the impulses towards the spinal cord, cathode has to be on this side, anode has to be here. If you put it the other way around, you'll only get the M response. You won't get the H reflex. Then you think, why don't I get an H reflex? I'm stimulating the nerve. Because normally it should go both directions. But because of the fact that generating with large current anodal block, it doesn't. So that's one problem. Second problem is electrical stimulation. In the first instance, stimulates A alpha fibers with the lowest intensity. A alphas are what? They are 1A, 1B, 1B, motor axon. They are called A alpha axon. So in the first instance, with the lowest current, you'll stimulate them. But considering that each nerve has A alpha, A beta, A gamma, A delta, and C fibers, so you really go, as you increase the stimulus intensity, then A betas. A betas are touch receptors, pressure receptors. A deltas, the pain, has fast pain, touch, temperature. And if you increase the stimulus intensity more, then you start to stimulate unmyelinated fibers, being slow. So this is how you stimulate, increase the stimulus intensity. That's how you affect these fibers. So if you want to stimulate, as I said to you here, we want to find out the pain pathway. How are we going to do it? If I increase the stimulus intensity slowly, A alpha, then A beta, then A gamma, A delta, A C, then I find I'm stimulating all kinds of fibers. And they are going all over the place, and we are recording the output. So what does it belong to? It doesn't belong to anybody. It belongs to alpha, beta, gamma, mixture of the whole. But there is a way. There is a way. There is always ways and means. How do we do it? First of all, if you want to study H reflex and motor axons with M response, you can stimulate nerve, mixed nerve, with a very small current, and work out this range and their circuitries. There's, of course, some problems with it, because A alpha and beta is about the same thickness, so they can intermingle a little bit. But motor axons are a little bit smaller, therefore you can really separate this from that a little bit. Anyway, but we want pain fibers, guys. We want this one. How do we do it? We use laser pulses. We use laser pulses because laser actually sends temperature pulses into the skin. Bang, bang, bang. It burns a little bit. In fact, when we do laser experiments, it smells like barbecue in the lab because it actually burns the skin. But we move the laser pointer a little bit at a time so that it doesn't actually generate. If you stimulate the same point all the time, it makes a little hole there. So it really makes a little hole. But we just usually put about a centimeter square area, so we just move it around so that we don't really generate permanent damage on people. So that stimulates these. They claim that this particular CO2 laser stimulates both of them, but slow pain fibers are so slow, it's like 1 meter per second. So you stimulate the toe, and recording from soleus muscle, for instance, by the time it comes to the spinal cord and goes back, it's 2 seconds. So you are looking at really, you can't, it would be the reaction time era. So you can't really measure them, a normal human person. But you can talk about the A delta circuitry, because A delta is about 20-30 meters per second range. So you can really talk about A delta circuitry, as pain circuitry. So that's fine. So by electrical stimulation, you can actually do that either A alphas or A deltas quite easily by using electrical or laser. But how do you work on A betas? A betas are very important, especially for the pain gate. It is supposed to close the pain gate. A betas actually can be stimulated mechanically. Probably that's what the stimulation of, maybe you've heard about the TENS, transcutaneous electrical nerve stimulation. So I actually put 2 far away electrodes on the skin, pass very small current between them, and you then stimulate those, A betas and A alphas. Because they are thick myelinated, they can close the pain gates, both of them together. So then that's, you can work out. But A betas alone is very difficult to find this pathway in human, because you can go this way, laser. Maybe you'll be clever enough to generate a way to stimulate A betas and find their circuitry. We've made it in jaw area. We've done some clever work on this. I'll tell you one example of it. For instance, periodontal receptors are A beta. They are Ruffini receptors. And to find their circuitry, what we did is we tapped on the tooth like this. And when you tap, and each tap is trigger, you record from the jaw muscles, you find out their circuitry. But you don't, because taps in the same time stimulate vibration sensitive spindles as well. And so you need to somehow, you tap first, find the circuitry using EMG, then locally anesthetize the tooth and tap again. So the difference between the before local anesthetics and after local anesthetic will give you the periodontal receptor contribution. So you can actually a little more lateral to work out, at least in your area of interest, the A beta circuitries as well. So I mean, this is really a question mark where somebody said, I used electrical stimulation and looked out A beta You need to say, how did you do that? Because electrical stimulation goes from A alphas. So how did you exclude A alphas? Tell me. If there is no answer, reject the paper. Right. So this is problems. I mean, if you are going to stimulate, for instance, okay, we talked about electrical. Mechanical stimulation also is quite useful. Mechanical stimulation. For instance, if you want to work out the stretch reflex, that's what we are doing with the arm. We think if we drop something very suddenly, we generate stretch reflex, right? For instance, for the deltoid. Do you really? When you drop things, many things happen. Okay, you stretch the muscle, but joint receptors, skin receptors, tendon organs, they're all activated. So why do you call it stretch reflex? Because 1A's, spindles, are the fastest conducting ones. So the first thing we see in the EMG, we say it belongs to 1A's. So that's why we say it's the stretch reflex. But if you look at it a little bit longer of 1A, that like we see it many phases of reflexes. Second phase, what does it belong to? We have no idea. It may actually belong to tendon organs, 1B's. It may belong to ratio inhibition because spikes already fired, so it may inhibit themselves. The only thing, actually, like the French guy who wrote that recent book on spinal cord with David Burke, Pierre de Seligny, they only trust 0.7 of a millisecond of the response when they give H reflex, for instance, A's belonging to 1A's. So after 0.7 millisecond of this PSTH on the H reflex, if you pass that, it could be anything. It could be 1B because it conducts a little bit slower than 1A. It could be ratio, because ratio cells are also needs one extra synapse. That synapse takes about 0.5 of a millisecond. So only the first 0.7, they call it 1A. The rest, question mark, big question mark. So in human, we are still digging, really, to find circuitries. It's not so easy. Anyway, we'll talk about that further when we talk about H reflex. So this is now the problem with electrical or mechanical stimulation. Let's put laser as well there, so that you can at least know that this is the mechanism that you can use. Of course, there is one other way, which is actually electrical stimulation, but it's called microneurography. Probably you've heard of that. This is sticking microelectrodes into human nerves. And in Sydney it's been done. In Scandinavia it's been done very readily in many places like Umeå and Stockholm. Anyway, that's all. The beauty about this is you really know which fiber you are stimulating in human. But also, in the same time, you can generate permanent damage on that fiber. I've done these experiments on myself. So one of my fingers tip doesn't feel anything. I think it's that one. Because I did this in Sydney, trying to learn it from median nerve. You put it into the nerve and find which area, as soon as you go into the fiber, you know which area is coming from. You feel that area. When you press that area, you get this action potential, like that. So if you stimulate that fiber, you know that you are stimulating a touch fiber, which type fibers are A beta. So A betas can be worked in that way. But it's very painful and causes permanent damage. Don't do it at home. I've done it. Look at me. Okay, so microneurography is also possible, but I prefer other ones, like electrical, mechanical, and laser is better for human pathway stimulation. So the pathway stimulation, you would just have to remember that it's not easy, and it needs to be really carefully thought. And when you're reading something, just don't trust it immediately, because it's not easy. So find out that if they really considered all these problems with it. Okay. So this is the input problems. Now we'll come into the output problems. Up until now, the input problems, any questions I can answer on this, and then move on to the output problems. Anything here? It's very clear, isn't it? Yes?
Yes.
All right. We'll go into the output problems. So I'll keep this here because each time we'll refer to that. So output, as we can only do input stimulation and output recording, and can do nothing about this one, we need to talk about motor neuron itself, because this is the final common output. So everything really happens in motor neuron. So if you draw a motor neuron, and its motor axon, and its fibers, it innervates. These are individual muscle fibers, it innervates. And this is the muscle. And with our single unit recording, that's what we do. Which you've all seen all these pulses. So, where does it all come from and why do we do it? A motor neuron receives up to 10,000 inputs. 10,000 inputs. And some of them are EPSP, this excitatory or synaptic potential, and some of them are IPSP, inhibitory or synaptic potential.
How do we know that number?
Roundabout 10,000, roundabout in general. In fact, people claim that it's a lot more than that, but let's stick to the classical view that input number is about 10,000. Now they're all coming from interneurons, from cortex, from the opposite side. So if you consider one of these, they all receive up to 10,000 inputs. So enormous circuitry. And what we are normally doing here is, if we draw now, this is time in milliseconds, and this is membrane potential in millivolts. Recording from inside, we put a needle here, a needle outside. We are recording the membrane potential. And membrane potential, or called resting membrane potential, which is about minus 70 millivolts. And when it reaches a certain threshold, which is about minus 45 in the cell, minus 55 in the axon, but let's talk about this. This is called threshold potential. And into the zero level, where the depolarization occur, and 30 millivolts, action potential goes up to 30 millivolts. So this is the normal situation. If you are recording from inside, if the motor neuron receives at the moment nothing, you just record it minus 70 millivolts, inside negative, outside positive membrane potential. If you let all these 10,000 do their jobs, then it looks something like that. It just looks like a noise. And if there's enough drive to bring it to contract that particular muscle, it reaches a certain level, a threshold level, and an action potential occurs. So this is noisy because of the fact that each one of these EPSPs and IPSPs are only generating between 0.1 to 0.5 millivolts, plus or minus. if it's excitation plus inhibition minus. So that's why, I mean, this is, as you can see, this is needing 25 millivolts. It needs hundreds of excitations to go up there. So that's why it's a very good integrator. Engineers will appreciate that. It's a good integrator. It integrates all the input, and it doesn't decide the first excitation comes into it, because once it fires, an action potential comes out of here, there is no stopping. Muscle has to respond to it, muscle will have to contract. So before it does all these calculations, and calculation is this. It's got a certain threshold, and unless it comes to the threshold, it doesn't fire. If it, for instance, comes to here, then goes down, nothing happens. As if nothing happened. It dies down. But if it goes up to the threshold level, it generates an action potential, then muscle fires, and we get these action potentials on the surface. Okay, so this is really the situation. And if we are wanting to contract that particular muscle continuously, which we do in our experiments, that's what it looks like. Then it's noisy, fire again. Noisy, we are sending, but drive is towards excitation. Excitation, so tease phenomenon. So it's like a saw. Is that right spelling? Yeah. Like a sawtooth. And that's what you need to imagine. When you see these, you need to imagine that there are these underneath them. Why am I saying that? Because when you give a stimulus, effectively, what you are really doing is synchronously activating however many axons you are activating into that motor neuron. When you stimulate the fiber here, that's what you are doing. If there is probably 10 fibers you are stimulating, all synchronously send EPSPs, or if it's an excitatory input, or IPSPs, it's an inhibitory input. So effectively, if your stimulus is here, for instance, effectively we are doing this. Inserting a larger EPSP than these 0.5, 0.1. So you generate tens of them, and if there's 10 fibers, and each one of them has 3 action potentials, so it probably makes you reach the threshold. But imagine that it was just like that. It didn't reach the threshold. So it's not useful. And if our stimulus is always that size, it can only affect this action potential only when, if it is given in this kind of region, very close to the about to fire level. If it's given during this period, it will do nothing. That's why, like we were doing in the experiments, that's why you don't always, each stimulus didn't generate an action potential. So it depends on where you activate. But if you are giving stimuli randomly, that means occasionally you will have it in that region. Because they are firing all the time, and you are giving stimuli all the time. So you will only affect the ones which are close to the firing level. I have to take this part off to show you what's really going on. I want to keep it, but there's no room. So what's really happening here is, if you draw it, if you all know geometry, I think, right? Yeah. Just think about like geometry. This is AHP, that one, this fold from the threshold. So this is threshold potential. This is resting membrane potential. This is about 10 millivolts. And our stimulus, if it is that big, well, even if you stimulate it randomly, eventually it will happen only this part. So this is X, and this is you can measure. This is you can measure. So this is ISI, inter-spike interval. So if you go ISI over AHP equals this, let's say, what we will call it, y over x. So by measuring this, you can work out the size of the EPSP you actually generated. Okay, so what we know here is this is 10. This is we can measure. If it's firing at 10 Hz, this is 100 millisecond apart, each spikes. And this we can measure where the peak occurring in the histogram, let's say 20. And then X will be 200 over 100 equals 2 millivolts. So that means this is only about 1/5 of the AHP. So this is 10 millivolts and that's 2 millivolts. This is how we measure, and we described this in 1989 paper, that how you measure actually the size of the given EPSP or IPSP. IPSP you can do it the same thing. It's a little more complex, but just stick to this EPSP just now. All right, so you've got 2 millivolt input. So that means if you draw histogram of this particular event, your histogram effectively looks something like that. Normal here again, after this one. But as the next one starts. So all these spikes, all these action potentials that were going to happen here, they moved to occur on top of each other. They all moved to this level because our stimulus happened to be here. I mean, relatively speaking, because they'll all be coming from different phases. If they come from here, for instance, it will not be affected. Our stimulus is here. If it comes from here, our stimulus will be affected. It will move from there to there. So always it puts it on top of the level where the stimulus is effective.
If what comes from there?
I'm sorry?
If what comes from there? You said if it comes from there, it will be affected. If what comes from there?
What comes from there? This is the stimulus.
Okay.
And if the stimulus is at this position, it moves all these spikes that would have action potentials that would have occurred here to occur where the stimulus is, where we inject this large peak, by stimulating all these afferents simultaneously and synchronously and affecting this motor neuron altogether. So that means now by looking at the size of this, by looking at the size of it and dividing it by the number of stimuli, you can also work out the size of the EPSP. So if this is, for instance, 20 extra, we call it extra spikes per trigger. If it's extra, what trigger is 100, so that makes it 0.2 extra spikes per trigger, which makes it 1/5 of the EPSP, AHP again, because it's 0.2 of this whole thing. This whole thing is 1, it is 10 millivolts, 0.2 of it is equals to 2 millivolts. You can work it out in many ways. So looking at the size of this, the maximum or silent period, you can call this area, but it's really not silent period. That's what I'm going to tell you. Because what you see here is really a hole in the histogram, not because there is an inhibition here, but because these spikes, which would normally occur here, they move to occur earlier by the extra EPSP, large EPSP is injected into the system. So that's why they moved forward. So this is not an inhibition. This is really where the spikes would have occurred if there is no stimulus, but they now moved forward. Phase advance, we call it. Phase advance generated that silent period-like events. And there are thousands, absolutely, paper on silent period. But I think they need to be silent soon. Because we are proving time after time that silent period doesn't exist, but there are still papers on silent period.
Calling it an inhibition, because that's what's wrong, eh?
That's right.
They can call it whatever they like, but
Well, it's not silent.
it's not an inhibition.
Yeah,
Yeah.
and also, yeah.
Yeah.
I mean, silence usually described as motor neuron silent, therefore there is an inhibition.
Yeah.
Okay, so where am I here? All right, I've done that. So now we need to get into the fact that we can give various stimuli in a trains and try and build up this particular system in a histogram, then into frequencygram. So what I'll do is I'll still need that one. I can get rid of this one if they're taking it down.
Mm-hmm.
Okay. So what I'm going to do now is give you trains of activation. So these are action potentials that we are recording from. From where? From there. So we've converted them sort of like acceptance pulses, looking like that. And you always have to imagine that this is what's really going to happen. This is really what's happening. The sawtooth phenomenon. Always remember that, then it will be very easy. So if I give the stimulus, for instance, here, if the EPSP is large enough, it will move this spike into there. So phase advance. When it moves spike there, of course everything will start from here, from now. So everything will shift. Okay, so I'll come to that, draw to histogram from this. So this is one, and if you do hundreds of these stimuli, for instance, and it will start from somewhere else each time. So I'll draw the histogram for this one, for instance, and we can build it up. So each one of these, this is now counts, number. This is, again, time in milliseconds. So we'll drop each one of these is acceptance pulses. Let's say this is 1. Drop down here, generated this. So it's really demonstrative, so that in the future everyone can follow this. So stimulus is given at this time, so I'll move the time a little bit. And then it regenerated action potentials, that and that one. Okay, so this is one time, n equals 1. So if we do many of these, now I show the stimuluses here. If you do another one, for instance, again the stimulus is given here. It will move this one now to there, if it's big enough, that is. And so there will be another one here. And it starts from here, so there will be another one here. Maybe another one there. That. So this is now 2. two of them. So you just imagine this happening hundreds of times. This won't always go up. For instance, in this case, we've got this. Our stimulus is given there. It generates an EPSP. It reached nowhere. So that would be there. That would be there. That would be there. So through this is 3 now. So if we imagine hundreds of these happening, that this is probably 10 counts. If we give, let's say, 50 stimuli, this may go up to 10. And these are all going to be full, probably up to about 2. And they'll probably not very precise hole here. Occasionally there will be spikes here. And there will be some more occurrences here. And then later on, looks something like that. So if we give about 50 stimuli, and this goes up to 10, and this goes about, depending on the bin width, it may go up to 2, for instance. So in this situation, when you look at this particular thing, then you say, okay, stimulus generated 10 out of 50 stimuli. 10 out of 50, it means 0.2, isn't it? So therefore, EPSP size must be, again, 2 millivolts. Right?
Mm-hmm.
Is that quite clear? So just giving this size can get you the size of the EPSP. But then you see other things. You've got, like, you call it excitation 1. So there's a silent period there. It's usually called inhibition 1. And because everything, or at least 10 of them, started from the same spot, it will generate a secondary and tertiary peaks. Not as big as the first one, but they are nevertheless bigger than the pre-stimulus bin count. So it will be called excitation 2, inhibition 2, sometimes excitation 3, inhibition 3. So if you see something like that, then you will say, if you imagine the first drawing I did, the wiring diagram drawing, that now from the stimulus to the effector, you've got a short excitatory connection, then long, little bit longer inhibitory connection, then another excitatory connection with that kind of delay probably going through the thalamus, then another inhibition maybe going through basal ganglia, and very long third excitation probably going through cortex, and so on and so forth. So because you find something, you have to explain it. That's what people did. So they imagine things going through cortex and many times going backwards and forwards, because they had to somehow put some reliable story to these secondary tertiary peaks and troughs. Okay, maybe they exist, but maybe they don't. Remember in the beginning I said to you that because we are working indirectly, our method has to be really perfect. Otherwise, you can't trust these findings. So when we probably in early 90s, when we started these, we were starting to look at this in EMG first. Each time we've done similarly in EMG, each time we get an excitation, we were getting inhibition, excitation, inhibition, and it looked as though to us that each excitatory connection followed by inhibitory connection, followed by another excitatory connection, and if it's an inhibitory pathway, it looked the opposite, and so on. So you start to wonder whether they were real or they were artifacts. So that's where we are coming now, to go from this kind of analysis, which we call it probabilistic analysis. It includes surface EMG and histogram, going to another level. But before we're doing that, we did, first of all, simulation studies. We thought, if we have regular firing motor neuron, which you can simulate, and if you inject just a single EPSP, what happens? We did simulations in the early 90s. And this is exactly what happened. Then we said, okay, if we give a single inhibition, what happens? Opposite of this happened, like similar to that. So inhibition followed by excitation, followed by another inhibition, so on and so forth. Because of the fact that you are displacing the position of these action potentials, which then start from another spot, generate secondary and tertiary peaks. When it generates peaks, it generates troughs. So therefore, several peaks and troughs. Even if you insert a single EPSP or IPSP into the simulation that you are doing. Okay, this was simulation, we thought. Simulations are nothing, and journals don't really were convinced about it. So I wrote to the Slice Center in Seattle. We were working on slice motor neurons. I asked them whether I can come over there and do this project where a regularly firing motor neuron in slices, if you inject single EPSP, what happens? Single IPSP, what happens? Double EPSP, what happens? And double PSP, followed by EPSP, followed by IPSP, what happens? So I went there 4 times, 2 months each, did these experiments, and which is the final report that I sent to you. That's up. It's a mixture of probably 4 papers, 2 journal physiology, 2 journal neurophysiology, all put together. The idea with that is that probabilistic analysis, because we rely upon where the position of the action potentials are, may be wrong. First of all, we've shown that this is wrong in our studies. Since in human we're working indirectly, I want to remind you each time, our method has to be correct. Therefore, when showing that this method is wrong, it should have been left in the history, but this is happening in the first paper we published in 1999, and 15 years after, people are still publishing histograms and surface EMG records, including some of us. Anyway, but we are, in the same time we publish surface EMG, histogram, and PSF at the same time, so that the comparison can be possible. So what we thought in the showing that this is wrong was one thing, but we need to really introduce a new method so that it's actually reliable. So what we thought at that time then, and by that time it's well known, that if we inject into a motor neuron current and record the discharge frequency from a motor neuron, there's a straight line relationship between the two. So if we insert more current, we get more frequent signals, less current, less frequent signals. So we thought, since we've got these as individual action potentials, we can convert them into frequencies and measure the current effectively on the motor neuron and find out whether they actually represent input EPSP or IPSP precisely. So what we did is, probably, which one should I get rid of? They're all very important. This one maybe. This will go. So now I'll convert this into frequency graph. Exactly the same thing. Did 3 times. And the stimulus is given here. Now the first one, and histogram, you've seen it there. Now frequencygram, this is discharge rate or frequency in hertz. And this is against time in milliseconds. So we take the distance between this action potential and this action potential, that's ISI, interspike interval, and 1 over interspike interval gives you the frequency. If this is, for instance, 100 millisecond, 1 over 100 millisecond gives you 10 hertz. Of course, it needs to be in seconds. So this is 0.1 of a second. So let's say this is 10 hertz. So we put a dot where the second event occurs, is 10 hertz. Then we measure the next one. It's a little bit faster, interspike interval slower, so it goes up a little bit. And so on and so forth. So we now have dots instead of positions where the action potentials were occurring. Those positions were wrong. But interspike interval converted into frequencies, it started to give us better ideas. So let's just put many of them. Let's say we've done 50 of them. The stimulus was here. Now we have higher frequency events occurring here because of the fact that we have phase advanced, like move that spike to there, therefore interspike interval became shorter, therefore frequency has to be higher. So you get high frequencies here, and then continue, for instance, like this. So eventually we found something like that. Now, if we insert a single EPSP, and we knew the size of shape of our EPSP, this is happening in slices. So that's what we've inserted. It looked something like that. A single EPSP we inserted, and we saw this. So almost as if it followed the input. Of course, I mean, it's just almost exactly followed the shape of the inserted current. Almost exactly followed. However, if you do this histogram at the same time, histogram, again, big counts here, and almost no counts or very little counts here, compared to the pre-stimulus, and then secondary big counts here, which were just same frequency, but a lot of spikes here, and then a little bit less, and another big counts here, but more 10 hertz spikes over there. So the frequencies at three times a standard deviation only went over that plus and minus 3 standard deviation only when during the insertion of this EPSP. And after that, it stayed within the plus and minus 3 standard deviation. Therefore, we said, okay, we found something. Not only we just rejected this previous as being wrong, but we found a new method, the frequencygram, that actually illustrates the exact shape of the inserted current into the motor neuron itself. Then we did IPSP, it did the same thing. We insert IPSP instead of EPSP. Something like that. So there is no secondary and tertiary events because the frequencies are exactly the same, but the number is high. So since we are dealing with frequencies, there is no secondary EPSP or IPSP, so the frequency stays the same. But if we insert, we have done these as well. For instance, IPSP followed an EPSP in the sliced neurons, then these would follow the same pattern. So we've done all kinds of them. Small IPSP followed by big EPSP, IPS, 3 of them, 4 of them, whatever. So if there was real in the circuitry, if there was 3 or 4 circuitries, it should come out using frequency ground. So we didn't just want to stop with one EPSP or one IPSP, because it could have been true that we could have secondary loops and tertiary loops, and we need to simulate those as well. So therefore we did, that's why I went for there 4 times, not just 1 time. Each time I brought 1 paper, and each time brought a new idea of the frequency ground actually works under almost any circumstances. So, okay, we'll with it. Okay, up until now I talked about the problems with the wiring diagram, measurements in human. Animals is fine, but they were anesthetized, there was problems with them. In human there were problems in input, selective input delivery and output. The problems, as we discussed here, that using a methodology other than surface EMG or histogram, it's a frequency ground. Then, up until now, I think we get through the questions. Then we can look at, for instance, the H-reflex work, then the TMS work, and criticize those as well. So, questions on this so far? If there are no questions, I'll go into the H-reflex first, then I go to TMS. No? All understood? So what's the difference between frequency ground and histogram? For instance,
looking at the histogram, you see several events after a trigger, whereas looking at the frequency gram, you only see one that's actually significant, or at least
you only
more
look
than
at
3 standard deviations.
you actually see,
above the
you
mean.
see there's a dense events here,
Mhm.
but they're all the same frequency. So therefore, when you see that, you say that there's nothing happening here. But whereas if you look at this event in the histogram, they'll sit on top of each other, it will look like an excitation. But frequency-wise, it's the pre-stimulus frequency the same as this frequency. Therefore, no extra thing must have happened, because frequency versus, that's what I've drawn, input current, illustrating a straight line relationship. Problematic is you missed the beginning, so okay. So H-reflex first. So H-reflex was actually trying to stimulate the 1A. Well, at least claim that it stimulates 1A, and generates 1A related. So you've got the 1A is coming from the spindles, and it's, of course it's got its and it's supposed to be monosynaptic, and we are recording on the surface. So this is the spinal column, of course, again. So we are recording either surface or intramuscular, this particular circuitry. Of course, if you stretch it, like we do for deltoid, I talked to you about that there were many other receptors will be stimulated, joint receptors, tendon organ, etc., etc. But the shortest loop belongs to 1A. Therefore, if you look at the EMG, I'll start with EMG. If the stimulation is given here, for instance, I will give, for instance, this is 50 stimuli. So after a certain delay, you get an H reflex. It's very sharp. Then it looks something like that. That's what H reflex really on surface EMG looks like. Okay, that's fine. You can find, as I said, Pierre de Slinge and David Burke consider only a very small portion of this is belonging to 1A. I'll come to that in single units. But just, you must have all experienced seeing this on H reflex. On a rectified, averaged EMG. That's not single EMG, it's rectified, average EMG. And a lot of the case, this is, in many articles, this is known as silent period. And this is H reflex, silent period. I just remind you that from the light of what I've told you so far, you can at least question this whether or not a real thing, unless and until you do single unit frequency analysis. If you do single unit frequency analysis and there is a frequency fall compared to the pre-stimulus frequency, then you can say, okay, there is an inhibition. But if there is no fall in the frequency, then you have to be doubtful about that this is an inhibition or generated by an inhibitory pathway.
All this what you have explained was for taking the example of one synapse, and we know that there are multiple synapses and stuff.
Exactly.
So
exactly. Well done.
would it?
I'll come. Well, let me say that. For instance, if guess what? If we prove that this is all true, this is E1, this is I1, this is E2. If we do frequency analysis and these are all correct, then this tells you exactly this. A short EPSP, okay, then long IPSP, probably in this circuitry somewhere here. And depending on this latency from there to there, you'll have to then imagine each interneuron takes about 0.5 of a millisecond. So the final one usually an inhibitory one. Then this, because it's such a long latency, had to go somewhere else, probably most likely to the cortex, and then come back. Then you'll have to imagine the conduction velocity here and conduction velocity back, and how many synapses it makes to make up for this latency. And then duration is quite long. That means it's a continuous event occurring. Maybe late 1As are generating more excitation and so on. So you have to somehow convince your journal readers these are all correct. But we are showing now that a single EPSP can generate the whole thing. So effectively we are saying that maybe there is only one circuitry. Okay? But if you do frequencygram and see secondary and tertiary peaks and troughs, then you are really legitimately have to go and explain them. But at the moment, what is explained so far in the literature may not be correct. That's all I'm saying. Because they have not shown it with frequencygram. We are starting to show it now, one by one. We have started with the jaws, with H reflex, but we'll be showing the MEP, for instance, including H reflex. So, in the H reflex, in the frequencygram, so if I draw it down here, so histogram is almost exactly the same as surface EMG, so I'm not redrawing histogram. Histogram and surface EMG are the same. But surface EMG is a little bit, I suppose, low-pass filtered version of histogram. Because as things go to the surface, we know that it becomes 10 milliseconds long. Therefore, histogram is more precise. Surface EMG is sort of less precise version of histogram. Okay, so single motor unit frequency point of view, this is, for instance, 10 hertz. The unit is firing at 10 hertz, and we've done 50 stimuli. It will look something like that, which does actually, we know. There's an increase there in frequency, and there's some small number here, and goes back to normal. And we did find that there's an inhibition here.
And that's
exactly what it looked like.
That's when it was an excitation on the histogram, right?
This is, sorry?
And that inhibition actually was occurring when there was actually an excitation in the histogram. So it was not a
exactly,
second, yeah,
exactly.
Yeah.
This is a lot of counts here. because inhibition actually becomes some of these action potentials delay to occur later. Some of these action potentials move forward to occur to make the peak. Some of them move there, so on. So, but they were real. So we had to explain, and that's what they said the shape we insert when we do an H reflex. But not because of the fact that you give the stimulus that it happens. We worked it out that this particular thing was a 1B inhibition because of the fact that when you give the stimulus, just after about 20 milliseconds later, you generate a twitch. And that twitch itself causes that particular 1B excitation. And we worked out that the latency of this and the start of the twitch actually gave you the 1B latency. So we worked it out that what we generated is really 1A, and it lasts longer than previously thought, and the silent period was really continuation of excitation because the high frequency events are there. Rare, but high frequency, therefore excitation is still continuing. And the fall in frequency is also genuine, not because our stimulus generated that as a secondary loop as such, but because of that twitch it generated. And twitch, we know that it activates tendon organs, and tendon organs inhibit the homonymous muscle. So effectively, we explained 2010 paper, I think this one. So gradually we are going through and reanalyzing all these what's been described in the literature using frequencygram as well as force. Force was almost never recorded in H reflexes. People just say this is H reflex, these are the pathways. But it's a secondary to the stimulus, secondary to the contraction. So this is what we've shown.
Well, the same question, like if we have, there will be multiple other synapses, what would be the effect of them? Like we are not, for example, in spinal cord, we would have other synapses, for example, coming on this last one. Here, exactly. So how they will affect, for example, on these?
All right, it would affect. The thing would affect most is you first of all ask subject to fire this one continuously. That's what you are the main thing. Yeah. So you've got a big cortical input going into this, firing it like this.
Nice.
Continuous drive is towards threshold. No matter what happens, it's going towards the threshold because of this input. And any other input going into this up to 10,000 input, remember, or these each one of them is, they are going to be affected, of course. But the main drive, the synchronous event, the biggest EPSP, say, out of all these, the biggest EPSP is generated through our stimulus. Because we are stimulating not just one 1A, but maybe 100 1A. And each one of them has got synchronous action potentials. So when they arrive there, they make a huge impact compared to the AHP. The other ones are only 0.1 to 0.5 millivolts. The other ones, they may not be significant, and some of them are inhibitory. That they actually generate a noise. Those other ones just generate a noise, but impact of the stimulus is huge in that noise. That's why we can separate the noise phenomenon out of the noise phenomenon. Because it's such a synchronous, so many axons are stimulated at the same time. So both summation is occurring at the same time. The little ones occurring here, that's the noise. They occur all the time anyway. And,
so like this, our input would not affect, for example, there is an inhibitory something, it would not.
If it's strong, for instance, if you are walking, your pattern generator, it actually affects the final, this one, presynaptically, inhibition. when you are walking. That's why you can actually, when you are walking, you can stretch muscles.
Yeah.
If you stretch a muscle, it wants to contract. So you will have to be, if stretch reflexes are working all the time, you can't move. You can't move. To move, as soon as the pattern generator starts, it inhibits it presynaptically, says, one ace, work, but I can't let you activate motor neuron anymore. So you can stretch the muscle easily if you can walk. Otherwise, walking would have been, or chewing would have been impossible if they always excited homonymous motor neuron.
So the inhibition or the excitation gets enhanced.
Not getting enhanced. It just inhibits this excitation. This still works. I mean, you stimulate, for instance, H reflex. We've done actually H reflex during walking. Becomes almost nothing, almost very small.
Okay.
So that it allows the stretch of the muscle during walking.
No, for me, a whole story is very clear when it's if I have one synapse in my head and all that makes sense. When I start thinking, okay, but we know that it's not only one synapse. There are multiple things going on. So what's happening there? Then it gets a bit confusing.
Just imagine that other synapses are just noise.
Okay.
That's all you need to see.
And our
because they are not synchronously stimulated, and our stimulation is actually that point. The rest are asynchronous and almost like noise.
And cancel each.
So they cancel each other out because they are happening everywhere compared to the point where we are analyzing them as a averaging point of view in that point. As you average it to the stimulus, everything else becomes noise. The only thing occurs because your trigger is following this one, then event is really represented by occurring at this trigger point. Rest becomes just noise. In fact, disappears, not even noise. So this is H reflex. I'm sure you are interested in H reflex. You know, I know that. But now we've done, for the first time actually, we are starting to see, which with Gabby we've done some with TMS stimulation and recording from the first dorsal interosseous, where we want to describe that silent period is not silent, which we did a little bit of this. But this, working on tibialis anterior, this becomes much more clear because you can see I1, I2, I3 quite separately. Not only actually we are introducing that I1, I2, I3 are genuine excitations in the light of we are rejecting the previous analysis, which only was shown with the surface EMG, all these I1, I2, I3. So they could have been the artifact of the first event. Mm-hmm. So we are showing that they are real. This is one good thing that we've got under our belt. The second one is that after pre and post treatment, what happens? I mean, this is really two fantastic findings. Even if nothing happens, we've got we can describe the I1, I2. So I'm expecting that it will be quite a good paper. With all the analysis coming from Samran, and probably today we are doing 3 experiments, but tomorrow and Monday we should just go through them.
Yeah.
As well as finish the experimental bearing research paper. The ball is with you on that.
Yes, Imran.
Thank you.
When you finish them, we can. Okay, that's all I want to say really, because the other one, the results are coming out. We can discuss that as we see what's coming out. Please ask anything you like, and so that we can discuss when it's freshly in your minds. Did you all get convinced that frequencygram is the way to go? Mm-hmm. So I convinced everyone. Matt as well? All right. All right then. We've done our job in that case. So you'll all be citing Kemal.
Do you want to do the TMS one, or do you want to? Are you brain full now?
I can do more.
Huh?
I can do more.
I'm happy to go. Do you want to explain the TMS? I don't think they necessarily know what I1s and I2s and
okay.
you
That's fine.
see, so
that's fine. Yeah.
Because it's quite amazing what we've
This
actually
is quite a
found.
good story, actually.
This study that we're actually collecting the rest of the data on now.
With the
It's
TMS
quite amazing, yeah. But it is also pretty complex.
So, we start from the probably black one. So the TMS stimulates the cortex, right? So this is stimulation, let's say motor cortex there. Now, in the motor cortex, and we are recording probably a little bit down here. We are recording from here, from the tibialis anterior, with the needles. So we see something like that. Okay, when you stimulate the cortex, first of all you generate, if the stimulus intensity is really high, or electrical, you generate a D wave. D wave is the direct wave, so it stimulates really the axon here, goes very speedily. If you record from the surface using, let's say, surface EMG, even though we know that the problems with surface EMG, let's say the stimulus is here, so certain latency after the stimulus, you see something, very short latency. So this is the D wave.
Don't you stimulate the upper motor neuron itself?
This is stimulating the motor axon at top in the motor cortex.
But it's really only a 2-neuron pathway.
Yeah, it is. I mean,
So I'd
too many.
consider the D wave
And this is
that one there, yeah.
something like that. Not even that. Sorry.
So the D wave is that first one, right? Yeah.
Yeah.
But you kind of want the other ones in there for the inhibitory.
So this is the D wave. Then you've got other ones which are really stimulating interneurons. That's what I believe. That's what it's looking like. Because it's nothing to do with this area. It needs to be happening here because it happens through the stimulus intensity. But they are only a few milliseconds apart. Therefore, it's really either stimulating this or stimulating that or stimulating the third one. So obviously, if it stimulates that, it's going to be another peak there. Only 2 or 3 milliseconds apart.
Yeah.
Then stimulus intensity increased a little bit more. It stimulates that one. The reason for that, I'll tell you.
Indirect
The
or
reason for
inhibitory?
Indirect.
Indirect.
let's just say I1, I2.
There is only always one DN.
The reason for that is, if you imagine the situation, just blowing it up here so that you can follow it easily. So this is the spinal cord. So this is our motor neuron going to the muscle. And this is the cortex, let's say. This whole thing is the cortex. If you stimulate it, you first stimulate the axon. Because axons have a much lower threshold. Probably I was mentioning that it was on the soma, it was 25 millivolts it needs. For the axon, it needs only 15 millivolts. So you stimulate the axon first. If you increase the stimulus intensity, then you stimulate this one. Let's say this is I1. If you increase a little bit more, you stimulate this one. But while you are doing all this, you are still stimulating all of these. But to be able to get action potential from here to there, you need to first of all generate an action potential here. Even if you get an action potential here, to generate an action potential here, you need, if it's an EPSD for instance, you need at least 100 of them activating this one, so that it generates an action potential here. So you need another 100 for action potentials to activate this one. So each time it becomes much more difficult. That's why, depending on the stimulus intensity, you get I1s and I2s and I3s. Because each time you are expanding one extra interneuron. One extra interneuron. Because each one for this one, for instance, when we stimulate that, to activate this, it needs to be synchronously activated, and many of these, not just one, many of these, all at the same time, activating this so that it can be activated. So it needs to inject 25 millivolts, at least, to activate this. So this is the same. They all have to be activated to generate an action potential in one of them. So it becomes more and more difficult as you go to further and further up in this circuitry. So that's probably why you have these, and that's probably why they are only a few milliseconds apart, because they are only involving one interneuron. Synaptic potential takes about 0.5 millisecond to cross across one synapse. So if you can imagine that's 2-3 centimeters, it may take about a millisecond to conduct. So it's right enough. And considering that this is only shown in this surface EMG is really low-pass version of real event. So that's probably why they are separated so long. But this is due to this fact. Anyway, what we have done is stimulating that and recording from single units. So far, we have seen in the histogram, we have seen, this is our stimulus. About 30 milliseconds later, we saw a peak, really large peak, then another peak, then maybe another peak, and so on, something like that. Is that right, or am I exaggerating? Well, this is histogram.
Yeah.
In fact, we saw a little bit dip here, didn't we?
Yeah.
Something like that. In the frequency gram, we saw, so this is frequency hertz, and this is number, PSTH, PSF, and something like that. And there is no inhibition at all. So either there's less number of spikes, which looks like inhibition in the histogram, because less number of spikes, therefore inhibition, compared to this.
I thought we saw a true cortical silent period, a true inhibition, but it was shorter than the one in the frequencygram.
Did we see inhibition?
Yeah.
I think we did saw
Yeah,
it.
because that's one of our main findings.
Yeah.
Remember, we confirmed that there is a real inhibition and it shortens
I
after
can't remember.
spinal manipulation. Yeah, I remember.
Oh,
I
right.
wrote
Because I don't remember the paper, but I do remember Heidi saying
Well, I
that-
remember because I wrote the paper.
No, because I remember that she's saying that we are confirming her own previous findings.
Yeah, we confirmed it. Big time.
Really?
Yeah,
From the
but it was,
surface side.
but it was a
But it was
From the
shorter.
surface,
I think it is somewhere here, wasn't it?
But it was shorter. The silence was shorter than
Wasn't it somewhere far away?
no.
Was it here?
Well, we didn't really have two spikes. We had one real big spike, one excitation,
and then
followed by an inhibition, but it was not as long as in the PSTH.
All
Because
right.
the PSTH indicated that it was a longer inhibition.
Show us then how it was.
It's okay. It's okay. It's
No, no.
Yeah.
No, I don't remember. If we have shown it, we have shown it.
We have.
Right, voila. What the frequency shows, we trust.
Yes.
We trust in God. No, we don't. We trust in frequency graph.
Can you do one more thing for me? If I mean that's just at least a brief one for you. But could you do me the H reflex and the V wave lecture again? You know, when you do the different motor neurons and how we electrically stimulate from the brain down, it stimulates in that order, and when we electrically stimulate it from that order. Am I pushing it now?
You are pushing it a bit. I'm tired.
Yeah, no, fair enough.
Maybe
Maybe we
Imran
have
Imran can
right.
tell us. Imran, you know all about V-wave.
I have the PowerPoint slide. I can
We
bring
can do
that.
another recording next week.
Huh?
Yeah, we can
another
do one with
recording
him right next week.
Yeah.
Maybe in the
No, not
afternoon.
next week.
Maybe in the afternoon. Yeah. Yeah.
To sit down.
Okay. Fine.
Maybe
Fair
start
enough.
to get numb.
Fair
Oh.
enough. That was a lot of.
Thanks, Kemal. This is amazing.
My pleasure, guys. All right.
Of that. Look at that.
We definitely confirmed that.
Comes-
I know.
we confirmed it in
Hey, turn
the.
that off.
Okay, let's
Yeah.
see.
You
I
shouldn't
thought we have
show me that
confirmed
I'm
it
sitting
in the
down.
EMG,
It is.
in the
I know.
PSF.
Yes, definitely in the PSF. In every single measure, we showed the